Hi students, welcome to Sunil's tutorial. I'm Sunil Milwani and today we'll be doing this chapter called as radiation. Take down please. Radiant energy is incident on a body. Radiant energy is incident on a body at the rate of at the rate of 2000 joules per minute at the rate of 2000 joules per minute if the coefficient of emission is 0.9 and the coefficient of reflection is 0.06. Find the radiant heat energy. Find the radiant heat energy first part of the question, absorbed. Second part of the question, reflected. And third part of the question, transmitted in 3 minutes. Now I know that for a body, coefficient of absorption is equal to coefficient of emission. That means therefore I can say coefficient of absorption is 0.9. Also I can say that coefficient of absorption plus coefficient of reflection plus coefficient of transmission should be equal to 1. So in that case I can say that 0.9 plus 0.06 plus T is equal to 1. So T is equal to 0.96. Right? Now they have given you that heat in incident per minute is 2000 joule. Heat incident per minute is 2000 joules. In that case, how much will be the heat absorbed? Heat absorbed will be nothing but whatever is the coefficient of absorption into the heat incident, right? You will come to know the amount of heat absorbed is going to be this, and this is your Q. Q is 2000 joules. Right, similarly they have asked you how much is the heat reflected. Heat reflected will be R into Q, and heat transmitted is going to be T into Q. You can multiply and get the answers. The answers for this should be 6000 joules, sorry not 6000, 5400 joules. This is per minute. You need to convert this into seconds, so you'll have to multiply it by time. Time is going to be 60 seconds. This is heat energy incident per minute. If I have to convert it into per second, I have to multiply it by time, and time is 60 seconds. So you'll have to multiply this by 60 seconds. All the three will have to be multiplied by.
The third one is the 3 minutes.
Per minute, no? They'll give you that in 3 minutes. So in that case, you will know. So in that case, there I didn't write the time here. Time is 3 minutes. 3 minutes is going to be 3 into 60 seconds. So your answer should be 5400, 360 and 240 joules. Next, take on next one please.
So this last day transmitted, first day would be 3 into 60 and the second day would be 60. Two that when he transmitted.
One is the coefficient of transmission. Find the heat energy incident. Sorry, heat energy is incident at a rate of. Heat energy is incident at a rate of. Heat energy is incident at a rate of 20 watts per second. On an opaque body having an emissivity of 0.8. Find the quantity of heat reflected in 1 minute. Find the quantity of heat reflected in 1 minute. Now, I can say for an opaque body, coefficient of transmission is 0. We also know that for a body, coefficient of absorption is equal to coefficient of emission. That means I will therefore get coefficient of absorption to be 0.8. Also, coefficient of absorption plus reflection plus transmission should be 1. So you will come to know what is the coefficient of heat energy that is reflected. Now, in that case, heat energy you got to find out heat energy. What are the answers to find out? Quantity of heat energy reflected, that is reflected, that is R into Q into the time. The time that we said is in 1 minute. So when you multiply this, you should get your answer. The answer for this should be 2400 joules.
So the reflected heat can be in negative also.
No. How will it be negative? Because this is 0.8, this is 0. This will be 0.2 only. Next, take on a metal sphere. A metal sphere cools at the rate of a metal sphere cools at the rate of 3 degrees Celsius per minute. When it is in a temperature of 50 degrees Celsius. Find the rate of cooling. Find the rate of cooling at 40 degrees Celsius if the temperature of the surrounding is 25 degrees Celsius. If the temperature of the surrounding is 25 degrees Celsius. Now, here straight away I can use Newton's law of cooling. According to Newton's law of cooling, if I apply Newton's law of cooling says that the rate of fall of temperature is K times the excess temperature over the surrounding, right? So in that case I can say that R1 is this, then similarly I can say R2 is K theta 2 minus theta 0, therefore R1 upon R2 is theta 1 minus theta 0, theta 2 minus theta 0, right? Cross multiply, you have R1, you have theta 1, theta 2 and theta 0, you should be able to get theta 2. Answer for this sum should be 1.8 degrees Celsius per minute. Next, take on next sum please. A body cools at the rate of 0.3 degrees Celsius per second. A body cools at the rate of 0.3 degrees Celsius per second when it is at 50 degrees Celsius. When it is at 50 degrees Celsius above the surrounding. What is the rate of cooling? What is the rate of cooling when it is 40 degrees Celsius above the surrounding? What is the rate of cooling when it is at 40 degrees Celsius above the surrounding? Here they haven't given you the temperature of the body, but they said that what is the temperature of the body above the surrounding. That means they give you theta 1 minus theta 0 and theta 2 minus theta 0. Same apply Newton's law of cooling. If I apply Newton's law of cooling, I'll get R1 upon R2 is theta 1 minus theta 0 upon theta 2 minus theta 0. All the data is given to you except R2. You should be able to get the answer for R2. The answer for R2 should be 0.24 degrees Celsius per second. A body cools at a body cools at 75 degrees Celsius a body cools make a correction, a body at 75 degrees Celsius cools, a body at 75 degrees Celsius cools in a surrounding of 35 degrees Celsius. A body at 75 degrees cools in a surrounding of 35 degrees Celsius. At what temperature will its rate of cooling be half that at the beginning? At what temperature will the rate of cooling be half that at the beginning? So straight away I could say that R1 is twice R2. Apply Newton's law of cooling. Newton's law of cooling. Newton's law of cooling is R1 upon R2 is theta 1 minus theta 0 upon theta 2 minus theta 0. Right? You can find out theta 2. Should be able to get the answer for this. Answer for this should be 55 degrees Celsius. Read down next one, please. A body cools from 75 degrees Celsius to 55 degrees Celsius in 10 minutes. At what temperature will its rate of cooling be? At what temperature will its rate of cooling be 1/4 that at the beginning? If the temperature of the surrounding is 31 degrees Celsius. If the temperature of the surrounding is 31 degrees Celsius. They've given you the initial temperature, guys, see this. They've given you the initial temperature, final temperature, time, and they've also given you the temperature of the surrounding. They've also given you that the rate of cooling at a lower temperature, that's at 55, is 1/4 that at 75. Now, they've said that a body cools from 75 to 55. So in that case, they've given you that it is cooling from this temperature to this temperature. That means what was the initial temperature of the body? The initial temperature of the body can be considered as the average of the two temperatures. Hence, here if I apply Newton's law of cooling, I can say that R1 is equal to K times theta 1 plus theta 2 upon 2 minus theta 0. Why did I do this? Because they are saying that it is going to cool from, it is not cooling to the surrounding temperature, but it is cooling to a different temperature. Had it been cooling to the surrounding temperature, then I would have said that theta 1 minus theta 0. But it does not cool to the surrounding temperature, it is cooling to a different temperature. It is cooling to a temperature of 55 degrees Celsius. Right? Now, I can also say that R2 is, what did I ask you to find out? At what temperature will its rate of cooling be 1/4 that at the beginning? So I can say R2 is 1/4 that of the beginning. I could say R2 is K times theta minus theta 0. That is the temperature you have to find out, where the rate of cooling is going to be 1/4 that of the initial value. Now divide the two equations. If I divide the two equations, I'll get R1 upon R2 is theta 1 plus theta 2 upon 2 minus theta 0 divided by theta minus theta 0. If you substitute the values, you have R1, you have R2 is 1/4 R1. The only unknown is theta, so you'll come to know at what temperature it is going to cool at 1/4 the initial rate. Right? The answer for this should be 39.5 degrees Celsius. Next, take on the next sum, please. A heated metal ball is placed in cooler surrounding if the rate of cooling is 2 degrees Celsius per minute, if the rate of cooling is 2 degrees Celsius per minute, when its temperature is 60 degrees Celsius, and 1.2 degrees Celsius per minute when its temperature is 52 degrees Celsius. Determine the temperature of the surrounding. Determine the temperature of the surrounding and the rate of cooling. Determine the temperature of the surrounding and the rate of cooling when the temperature falls to 48 degrees Celsius. Also find the temperature at which the rate of cooling is 0.6 degrees Celsius per minute. Let's consider Newton's law of cooling. Newton's law of cooling says that the rate is K times theta 1 minus theta 0, excess temperature of the body over the surrounding. So I can say that R1 is K times theta 1 minus theta 0. Similarly, I could say that R2 is K times theta 2 minus theta 0. Therefore, I can say that R1 upon R2 is theta 1 minus theta 0 upon theta 2 minus theta 0. The only unknown there is theta 0, so you will come to know the temperature of the surrounding. Next part of the question is determine the temperature of the surrounding, we did that, and the rate of cooling when the temperature is 48 degrees Celsius. I have to find out the rate of cooling when the temperature is 48 degrees Celsius, for which I need to know the value of K. From here I will come to know theta 0. Substitute that value of theta 0 in the equation. R1 is equal to K theta 1 minus theta 0. So from this equation I will come to know the value of K. Once you come to know the value of K, then you can find out R3. R3 is K theta 3 minus theta 0. From this equation you will come to know the temperature at which the rate of cooling is 48 degrees Celsius. No, you will come to know the rate of cooling at 48 degrees Celsius. And the last part of the sum says that the temperature at which the rate of cooling is 0.6. So, just call this as R4, guys. Just make this correction. Just call this as R4. Right? Now, the rate of cooling is 0.6. I want to find out the temperature at which this happens. Theta 4 minus theta 0. So from the first equation you will come to know theta 0, from the second equation you will come to know K, from the third equation you will come to know the rate of cooling when the temperature is 48 degrees Celsius, and in the fourth equation you will come to know the temperature at which the rate of cooling is 0.6 degrees Celsius. Right? Your answers for this sum should be theta 0 is 40 degrees Celsius, then you can find out R3 as 0.8 degrees Celsius per minute, and you can also find out theta 4, which is 46 degrees Celsius. Right? Take down next one, please. A metal cube cools from a metal cube cools from a metal cube cools from 60 degrees Celsius to 52 degrees Celsius in 5 minutes, and to 46 degrees Celsius in the next 5 minutes. And to 46 degrees Celsius in the next 5 minutes. What will be the temperature in the next 5 minutes? Now, we know that rate of by Newton's law of cooling I can say that the rate of cooling is K times theta minus theta 0. So here, since the body is not cooling to the surrounding temperature, I have to take the average of the two temperatures. In which case, I can therefore say rate of cooling. Rate of cooling is going to be nothing but theta 1 minus theta 2 divided by T. The rate of cooling is equal to K times the temperature that it is cooling from 2. It is cooling from 60 to 52 divided by 2, average of that temperature to the temperature of the surrounding. So this is going to be my rate of cooling. Generally here in all the previous sums I have written R1. Question: so why haven't you written R1 here? Because that used to be in terms of unit time. Either it was unit second or unit minute. Here, since they've given you in terms of 5 minutes, therefore I am taking it this way. So from here you will get an equation. Now they've also said that it cools from 52 to 46. So I can therefore say that theta 2 minus theta 3 upon T is equal to K theta 2 plus theta 3 upon 2 minus theta 0. Right? If you divide the two equations, this is your equation 1, this is your equation 2. If I divide the two equations, I'll get the value of theta 0. Now they've also asked you that what will be its temperature in the next 5 minutes, right? Let's assume let the temperature in next 5 minutes be equal to theta 4. So that means it is going to cool from theta 3 to theta 4. So theta 3 minus theta 4 upon T should be equal to K times theta 3 plus theta 4 upon 2 minus theta 0. So you should be able to get the value of theta 4, because by now you would have got the value of theta 0, and you also need to know the value of K. Wait, what we'll do is first we'll find the value of K. I can find the value of K by substituting the value of theta 0 in any one of the equation. Substitute theta 0 in equation 1. Suppose if I substitute theta 0 in equation 1, I will get the value of K from there. Right? Once you have the value of K, then you can say that theta 3 minus theta 4 upon T is equal to K times theta 3 plus theta 4 upon 2 minus theta 0. So you will come to know the temperature that it will cool to in the next 5 minutes.
So,
Ah.
how do you get the temperature when you take the mean?
It is cooling from, say, let's assume from 60 to 52. So what was the mean temperature that it is cooling from? Its initial temperature was 52, the final temperature was, initial temperature was 60, final was 52. That means it should have been somewhere around 56. Right, the average temperature of the body with respect to the surrounding is 56, so we always take the average temperature. If the body is not cooling to the surrounding, then we take the average temperature of the body. The answer for this sum should be theta 4 is 41.5 degrees Celsius. Next, let's see the next sum, guys. A body cools from 72 degrees Celsius. A body cools from 72 degrees Celsius to 60 degrees Celsius in 10 minutes. A body cools from 72 degrees Celsius to 60 degrees Celsius in 10 minutes. If the temperature of the surrounding is 36 degrees Celsius, how much time will it take to cool from 60 degrees Celsius? How much time will it take to cool from 60 degrees Celsius to 52 degrees Celsius? How much time will it take to cool from 60 degrees Celsius to 52 degrees Celsius? I want the body to cool to 52 degrees Celsius. Now let's see this. Apply Newton's law of cooling. If I apply Newton's law of cooling, then first thing they've said that the body cools from 72 to 60. So the rate of cooling will be equal to K times the average temperature of the body over the surrounding. Right? So here I know theta 1, theta 2. I don't know K and I don't know T. I don't have two variables. Okay. So in that case I can say that in 10 minutes. Okay. T1 is given to you in 10 minutes. So I'll come to know the value of K when I solve this equation. Right? Once you have the value of K, they've said that how much time will it take to cool from 60 to 52. That means here I'll get the value of K when I solve this equation. I want to cool from 60 to 52. T2. K times the average temperature of the body over the surrounding. Right? You'll come to know the value of T2. Because K you would have already found out from here. Theta 2, theta 3, theta 0. All the three temperatures you have. The only unknown is T. You should get the value of T. The answer for this should be 10 minutes. Next, two spheres of the same material, have their radii in the ratio of two spheres of the same material have their radii in the ratio of 2:3 they are heated to the same temperature and kept in the same cool surroundings. They are heated to the same temperature and kept in the same cool surrounding. Compare the initial rate of loss of heat. Compare the initial rate of loss of heat and the initial fall in temperature. Now they have given you that for two spheres. I can say for a sphere area is equal to 4 pi r square. That means now if I apply Newton's law of cooling, by Newton's law of cooling I can say that the rate of fall is directly proportional to area, temperature of the body over the surrounding, right, where area is going to be a constant term. So therefore I can say that R1 upon R2 is equal to A1 upon A2 into theta minus theta 0 upon theta minus theta 0. Excess temperature of the body over the surrounding. The only thing is that they are heated to the same temperature, they are cooled to the same temperature. That means theta and theta 0 is same. The only thing is that the radii are different. Therefore I can say that R1 upon R2 is 4 pi R1 square upon 4 pi R2 square, right? So in that case you will get R1 upon R2 is R1 upon R2 the whole square, right? So you will come to know the ratio of the rate of cooling. Now they have asked you that compare the initial rate of loss of heat. So we've done that. The initial rate of fall of temperature, right? Now rate of fall, that means with respect to time. So you will say let d theta by dt be the rate of fall of temperature. Right? In which case I can say that the rate of loss of heat is mass of the body, specific heat into rate of fall of temperature. Right? So in that case I could say that mass of the body. How do I get the mass of the body? We know, guys, that density is nothing but mass upon volume. Therefore I can say mass of the body is density into volume. Now volume of a sphere is 4 by 3 pi r cube. So this will be density into 4 by 3 pi r cube. Density of the body into volume of the sphere, right? So in that case I can say that rate of loss of heat, that is R1, is equal to mass of the body into specific heat of the body into rate of fall of temperature, that is d theta by dt 1, right? Rate of loss of heat is also equal to mass of the body m2 into s into d theta by dt 2. Why have I kept s constant? Because they have given you right in the beginning of the sum that the body is made up of same material, right? In which case now I can say that, in which case you can say that R1 upon R2 is nothing but m1 d theta by dt1 upon m2 d theta by dt2. They've asked you to compare the rate of loss of heat, right? No, they've asked you to compare the rate of fall of temperature. That means I can say d theta by dt1 upon d theta by dt2 is equal to r1 upon r2 into m2 upon m1 cross multiply, right? In which case I can say that this is equal to r1 into m1, r1 into m2. M2 is going to be mass. We already said that mass is density into 4 by 3 pi r1 cube, right? Similarly, I can say that r2 density 4 by 3 pi r2 cube, right? Since the body is made up of same material, density is going to be same, so rho is going to be same. So in this case, this is going to be nothing but r1 upon r2 into r1 upon r2 the whole cube. That's how you will compare the rate of fall of temperature, right? So when you solve this, you will come to know the rate of fall of temperature. See now next time, the answer for this should come to, answer for the first part is going to be r1 is to r2 should be 4 by 9, and second part rate of fall of temperature d theta by dt1 is to d theta by dt2 should be equal to 3:2. Take down next one please. Calculate the temperature of the sun and moon. Calculate the temperature of sun and moon given that lambda m is 4,753 Armstrong units, and this is for the sun, and lambda m for the moon is 14 times mu. Where lambda m is the wavelength of maximum intensity of radiation. Where lambda m is the wavelength of maximum intensity of radiation. Now, guys, if I use Wien's displacement law, by Wien's displacement law, I can say that lambda m into T has to be equal to constant, right? And this constant value is 0.2898 into 10 raised to minus 2 meters Kelvin. Now, once you have this, then you can find out. I can say for sun, they've given you lambda m as lambda m is 4,753 Armstrong unit, which can be written as 4,753 into 10 raised to minus 10 meters, right? Now, once you have this, then I can find out the temperature, guys. I can say that temperature of the sun therefore will be 0.2898 into 10 raised to minus 2 upon lambda m. That should give you the temperature of the sun. Now for moon, they've given you that lambda m is 14 microns, right? So that means for moon this is 14 into 10 raised to minus 6 meters. Once you have this, then I can find out the temperature of the moon, 0.2898 into 10 raised to minus 2 upon lambda m. That should give me the temperature of the moon, right? The answers for this sum should be 5824 degrees Celsius and minus 66 degrees Celsius, right? We will stop this here for the day. Thank you very much.